It's been a while since you heard from me, hey? I wanted to make a video, series of videos on gravity because I think gravity is one of, if not the most fascinating mathematical concept and is the thing that brought me into math, physics in the first place. I'll tell you why actually. So when I was a kid, I had a problem with deciphering video game or fiction from reality. Don't ask me why, I don't know. But in that, I had a game called Wipeout, which was a game about racing these hovercraft things that kind of hover off of the ground. And as a kid, I really wanted to see these in real life. I really wanted to go and see them. So I asked my dad one day, can we go and see them? And of course, he said no. And I asked why, and he said, well, it's not possible. And I'm like, why isn't it possible? And he couldn't tell me why it's not possible. I mean, it's not too intuitive to say why something can't defy gravity. It's just, it can't, you know? And that was kind of what sparked the curiosity or the interest in me about what gravity actually was. So I could answer that question. I could answer why it's not possible, right? Um, but yeah, so today is kind of like this intro video I'm gonna do. I'm not gonna jump straight into the theory of general relativity because it's very, very hard and very complex, and even I don't fully understand it yet. And it requires a lot of maths. There's a reason why it's typically a third year module in university. Um, there's a lot of supporting mathematics. Like, you could start with vector calculus, move on to differential geometry, and get to general relativity fairly simply. But we're going to start simple. We're going to start from Newtonian gravity, because you'd be surprised that there's some parallels between, this idea of space time, general relativity, and Newtonian gravitation. I mean, after all, Newton's laws are where it all came from, right? So, yeah, first of all, I kind of want to preface the mystery of gravity. I want to talk about what is it? Now, I'm sure you've probably heard before that it's not a force, but what does it mean for it not to be a force? It's always said that it's not a force, it's the curvature of space-time, but then what is that acceleration that everything feels towards everything else, right? Well, gravity intrinsically is mass energy curving space-time, right? As described in something called the Einstein field equations, which we'll come to later. But that acceleration, where does that come from? Well, space-time, think of it in your head, right, is composed of both a space portion of coordinates and a time portion of coordinates. So you'd have x, y, z and time, right? A four space, right? Four-dimensional space. Now, objects are, of course, latently moving through there. Even if they're not moving through space, they're always moving through time. Also, we think, of course. There may be exceptions to that I'm not aware of, but as far as we know, everything is moving through time. So everything is moving through space-time, and thus every object is going to have this path through. But if space-time is curved, as it is by mass, then what are those lines going to look like that objects take? In curved space, parallel lines can meet, right? As unintuitive as it sounds. So if two objects, for example, are passing through curved space and their parallel lines intersect just because they're passing through time, then they're going to touch in the spatial component of space-time, and thus they're going to touch in real life, right? And that's going to be what the acceleration of gravity is, and why objects come together is not necessarily a force. It's just a result of Newton's first law. An object will remain in motion unless acted on by an external force. But we'll come back to all of this later because there's a lot of supporting maths behind this. We're going to start simple with Newton's general law of gravitation, right? So we're going to start with the force vector field is equal to gravitational constant times the mass of the attracting object and the mass of the object generating the attraction, and that's going to be over r squared. And of course we're going to have to do the vector as well. The negative vector is negative because we're going towards the source of the field. Of course the vector of the field is going to be pointing outwards, so we're going to have negative because we're going towards it, right? Yeah, so of course then we can rewrite this because the gravitational vector field is equal to the constant times the mass of the attractor over r squared. We can rewrite then this overall force vector field as the mass of the little object that's being attracted times g. Of course, times, well, I gotta write the vector there. Times the gravitational field g, right? So that's F equals mg. You might have seen that before. Of course you have. Weight equals mass times gravitational field strength. It's the same thing, right? Now, what we're going to do is something a little bit different here. You may not have heard of this before. You may have heard of gravitational potential, but how can we relate this to our theory of general relativity? We're going to be moving on to something called the Newton-Cartan Theory, which is a space between Newtonian gravity and general relativity. It's like an interim, a middle point, and I think it's genius, right? So our gravitational potential is given as phi, right? I'm pretty sure that's phi. Correct me if I'm wrong. And this is going to be a scalar field, not a vector field, right? It's a scalar field that's going to be much smaller the closer to the generating mass of the field, and bigger the further away it is, right? As we know from gravitation, or as we know from potentials in general, electric potentials, whatever. Now we're going to take a mathematical operator called the Laplacian of this phi, right? That's going to be denoted as an upside down triangle. What does that mean though? Well, if we track a potential scalar field in 3 dimensions, we're going to see it gives us a dip, right, where we're close to the object, because of course the number's getting lower there, getting higher the further away you get. That makes sense, right? The Laplacian of the scalar field will give us a vector field. It's a bump detector, right? If it detects a negative bump, a bump going downwards, it's going to produce vectors away from that bump, and if it detects a bump going upwards, it's going to give us vectors towards it, right? So by giving this Laplacian, we're getting a field that's kind of the opposite of a gravitational field, because the vectors are going outwards. So if we take the negative of this Laplacian, we get a field that's going to kind of look like, I'm terrible at drawing, it's going to look like this, right? And this is starting to look familiar, right? Because this is what a gravitational vector field is. So we can define then the gravitational vector field as the negative of the Laplacian of the gravitational potential, right? And further upon that, we know that the divergence, which is, again, in this context, the divergence is again the upside down triangle with a dot next to it this time, beautiful dot. If we have a source of a vector field and arrows are going in, then that's going to give us a negative divergence, right? So the divergence is going to be less than 0, right? Oops, less than 0. If arrows are going out, it's going to be greater than 0, right? That makes sense. And if arrows are generally going in and out equally, then it's just going to be 0, right? That makes sense. So the divergence of gravity is given as a formula which we can come back to in a later date. 4 pi g rho, where g is the gravitational constant and rho is the mass density of the object causing the field, right? We can replace then the gravitational field with our previously derived minus Laplacian of phi is then equal to this minus, sorry, that's a minus 4 pi g rho, because it's a negative divergence, right? And if we cancel the negatives, right, we get then the divergence of the Laplacian of phi is equal to 4 pi g rho. And this is our first step to the Newton-Cartan theory of gravity, in that we have this field that's symbolic of a curved space-time, and we have an equation that's talking about gravity in terms of that curved space-time. The next step is the geodesics of this curved field, which is what I was just talking about before with the intersecting parallel lines. But for that we need a bit more advanced maths. We're going to dive into something called the Christoffel symbols, which always confuse me, so I'm going to make sure to doubly understand that before I make this video. And we're going to move into, geodesics. So yeah, I didn't want to go too crazy on this first video about this topic, but please do tell me if you misunderstood anything, or if I've got anything wrong, because I'm sure there must be something, right? But yeah, I'll hopefully be making that second video soon. But yeah.